some example problems. So I've got that. I also have a couple of example problems that we're going to look at for a variety of other reasons. But I also thought it would be fun to kind of show you guys that physics shows up in a lot of different places. And one of the places that I always loved watching physics, and in fact, there's actually a guy that I know that does a whole physics demonstration / show on cartoon physics. And and I am a fan of the Roadrunner and Wile E. Coyote. I really like the Roadrunner and Wile E. Coyote. And in mechanics, Wile E. Coyote, he has a real problem with physics. He's got a huge problem with physics. So kind of give you a couple of different ones. This one, we've all seen the lovely Roadrunner. And the Roadrunner likes to go to the edge of the cliff. And the Roadrunner seems to get away with everything, but Wile E. Coyote gets to the edge of the cliff, and we all know what happens. Physics actually works for Wile E. Coyote in this case, and he ends up falling. So you end up getting the curse splat because the Roadrunner has taken him to the edge of the cliff. The other places that Wile E. Coyote, where he usually has problems with physics, is things like this. We talked about us compressing the spring and putting in potential energy, and we're actually going to do a spring compression problem today. And normally this would work, right? We know what's supposed to happen, and I'll actually let this one run. We know what's supposed to happen. He's actually going to compress the spring, and he puts in the potential elastic potential energy, and we know that the spring is supposed to, when the Roadrunner passes by, there he goes, and it's supposed to eject him out just like the spring in a pinball machine, or the spring in a gumball machine, or the spring. But most of us know what really happens to Wile E. Coyote. He ends up getting tangled up in the spring to begin with, because he does have a problem with physics. So I will get you guys a link to this particular blog. It's got some really cool kind of walks through in terms of energy and certain systems. And they've got how a bicycle comes off by using a spring load. Again, we're going to do a spring load problem here in a little bit. And you can see how they actually get started up the hill because we've actually pushed in a spring, and we've used that spring to convert from potential energy to kinetic energy. You can do it in a lot of different places that are base jumpers. We're converting potential energy to jump off the cliff and hopefully have the parachute open. If it were Wile E. Coyote, we know what his parachute does. It doesn't open, or it opens at the very last minute as he's already hit the ground. Then we use stored energy a lot. We use it in terms of slingshots. We use it in terms of spring loaded for pinball machines. We use them for a lot of different places. We actually utilize that potential energy to help us out a great deal. So we can put it in there as stored energy and work through it there. Then we have our non-conservative forces, in that the friction is going to take some of that energy and convert it to heat, and we're not able to get all of the energy converted into motion. And one of the problems I'm going to do today, we're going to actually calculate how much work had to be added into the system to overcome friction. So we're going to actually do one of those type problems. And you've got some potential energy, like the transfer of kinetic energy to potential energy, and we have a human catapult. You can actually calculate how high the person's going to go up, and we'll actually look at that problem with our spring problem here in just a bit. So I will actually give you guys the link to this particular blog, and it's really kind of nice that you can actually walk through it and actually see some realistic problems. Let me do that before I forget. All right, go to Blackboard, my classes, so that way we have it all in there. Okay, I want to go not there. Okay, this is interchange. There we go. I've somehow closed no. Force tools, no. No. There we go. Now I got everything. What happened to all my stuff? Web link. And even though it looks like I uploaded Wednesday's video, which I did do, I did upload Wednesday's video, but it looks like I've got a duplicate. And so right now, if you go to click on that link, it takes you nowhere. And I will try and figure that out later today. So here's the energy blog that I just kind of walked through and showed you. Maybe. There we go. All right. Yeah, right now, if you click on this link, that's what it does. I will see if I can get that fixed. That's Wednesday's lecture. I'll see if I can get that fixed and hopefully get today's lecture in there as well. And let me see. This is one that's kind of cool. So you can see a practical application of using stored potential energy. This is a Pinterest on how to make rubber band guns. And then putting in the spring to actually convert the energy into the gear. And you can actually, so you can look at a variety of rubber band guns, but they bring in, this GIF will actually show if I retract the trigger, it pulls back, it allows the gear to move down. So we can either use the gear to release, or we can use the gear to actually add energy into the rubber band, which we're going to use that stored potential energy in order to do whatever projectile that we're doing for a rubber band gun. So you've got lots of interesting little rubber band gun pieces. Same thing happens in a bow. Even though we don't necessarily think of a bow as a spring, but that's exactly what it is. It is a spring. And when we're pulling back the string in the bow, we're putting in potential energy, and it's going to work very much like that stored potential energy in the spring potential. Crossbows use a couple of different places because they can actually put the spring in the trigger mechanism as well as the spring in the bow itself. So you can actually look at different pieces. So from a practical standpoint, we use potential energy a lot. And if you want to look at, I was kind of going through a whole bunch of GIFs this morning to see what kinds of GIFs to actually kind of relate some of the stuff that we've been looking at in terms of potential energy. You can actually come in here and play it. Here's like the trebuchets and the pumpkin launchers. Pumpkin launchers are great this time of year. Pumpkin catapults. There's some places that do engineering pumpkin catapults. They've got GIFs out here where you can have the roller coaster go, and you can actually see if this one will actually run for us. Oh, that one's not actually running for us, but there's one in here that you can actually see the transition. This one definitely did. Nope, that wasn't it. Yeah. Oh, we're not supposed to write. All you're seeing is the class. Was why didn't somebody say something?
We didn't know if you were just talking or not.
No, well, we can go through this again. It's all right. You should be seeing the computer.
Yeah, there you go.
All right, well, we'll go through it again. Because I mean, come on. Watching cartoons on a Friday morning is great, right? It's not Ren and Stimpy, but it's, so let's go back here. Where's my GIFs? Oh, shoot. Okay, we'll go back here. This is my Wile E. Coyote with his little spring problem. Where'd he go? Right there. Oh, you just passed it. There he is. There's my Wile E. Coyote with his spring problem here. So I got Wile E. Coyote with the compression. Unfortunately, this one doesn't go all the way through because if anybody's remember ever seeing this particular cartoon, we know what happens to him. He ends up inside the spring. And then afterwards, he kind of looks a little odd. He definitely looks a little odd after that. Poor Wile E. Coyote, he doesn't fare too well a lot of the time. There's the Roadrunner with potential energy. I think they actually have the one where he goes splat in here. Yeah, Roadrunner can defy gravity a lot, but Wile E. Coyote doesn't defy gravity, unfortunately. So we've got that one. So that one, the Roadrunner's got potential energy, and then Wile E. Coyote goes to the edge of the cliff, and he always falls down. So we've got a variety of things. So that's somebody's gaming that you can go back and play with the gaming stuff, because these are actually fairly easy to calculate. This stuff, the potential energy to the other is fairly easy to calculate. So we're talking about the bow being, it's not gonna let me. The bow being a way to store energy in the spring. Now my spring, when I store energy, I can store it two ways. One is by stretch and one is by compression, because if I do it in the stretch, the spring wants to go back. And you can see, like in this one, see if this one will let me go. No, not going to let me go to it. But if you go in there, you can watch the change between the potential energy to kinetic energy and back. And then roller coasters are all about energy. Roller coasters, that's why we take the roller coaster to the top of the first hill, and then we bring it in, and then we go back and forth with the roller coaster. So this is from Emperor's New Groove. You know, when they go into the gate. So if you've never played with it, and these are kind of fun, where you're looking at the low racetracks and the high racetracks are the same, because I'm putting in the same amount of energy, and it's a state function. It all matters where I start and where I finish. So we can look at different pieces along the way. So here's your roller coaster physics. We start up. We get potential energy, come down, we get kinetic energy, and as long as we're doing things, we get the loop-de-loops, and we start all over again. So roller coasters, transfer of energy all the way around. Now, granted, we lose some to friction, but we end up getting a variety of different pieces. So for you guys over in Tonkawa, here's the blog that I attached to to Blackboard. So this is a device that when they take the bike that they use, they convert the potential energy from the spring to kinetic energy to help them up the hill. And we've got our stored energy for the base jumpers in order to have it go. Then we've got our stored energy in our slingshot in terms of the rubber piece. But that could also be the spring and a spring pop gun, which we're actually going to do a spring pop gun problem. And this shows our non-conservative forces with the sliding of a cat. Good use of a cat, you know, and the cat's probably enjoying it. There's actually one, if you really like cat videos and dog videos, lots of spring launchers for dogs, where the dog can drop in the ball, press a paddle, and set it in, and the spring will launch the ball, so the dog can actually play itself to death if it wants to. Yeah, we can do that. And then here's the human catapult. You got two people off the bottom, ejecting the person up on the top. Again, it's all conservation of energy problems that we've got working on there. And we're actually going to do a problem very similar to this one, except we're going to do it we're going to actually calculate how much energy went into the friction for that system there. So my apologies, you guys need to speak up, you know. We did talk about, let's see, here's the rubber band. Let's see if I can find my rubber band problem. Oh, here's the rubber band gear. Oh, I want to go back. There's that one didn't go for where I wanted. There it is. There's the gear for putting in the rubber band. So for a rubber band gun using the spring. All right, so now let's play with some problems. Now we did some fun stuff. Let's play with some problems. Watch some cartoons, you know, get us going. And Wile E. Coyote had lots of problems with physics, you know, total problems with physics. He in physics didn't do real well. Okay, so let's do a simple problem to start with. And we're actually going to see this problem again. When we get to rotational motion, I've got an inclined plane here, okay? And I've got an object on an inclined plane. And this is one of the reasons why I'm going to do this one this way, because we're going to see this one again. Let's imagine that that is a can of soup. All right? And that's a can of soup, and I'm going to say it's a can of tomato soup, or it's a can of cream of celery, or it's a can of cheddar cheese soup. If I go to a Campbell's and I get that soup, and I'm using those as an example for right now, because those soups, if I open up the can, what do we know about the contents of that soup?
It shifts.
Well, it shifts, but if I'm using tomato soup or cheddar cheese soup or cream soup, it's kind of it's a gelatinous solid, right? It's not like if I open up a can of beef broth, or if I open up a can of minestrone soup, where the contents are real liquidy, right? The real liquidy. And the reason I'm choosing that kind of a can of soup, because that kind of can of soup is only going to do one of two things. It's either going to slide down the inclined plane, or it'll roll down the inclined plane. And if I do it as a solid soup rather than a semi-solid soup, because we all know it will droop and ooze, but if I do it as a solid soup, it's going to do more of a slide down the plane. What we're going to see when we get to rotational motion is that there's a difference between just sliding down the plane and rolling down the plane. And there's a difference between whether or not I have a solid object, or if I have an object that has, like chicken noodle soup, that's very fluid and can move around a lot. So this problem, what we're working with right now, is going to be strictly a slide down the plane. We're not going to have any rolling or rotational movement. But when we get to rotation in a little while, we're actually going to change it up a little bit, and we're going to let that can of soup roll down the inclined plane. So if I want to know the speed at the bottom of this inclined plane, and I'm going to have that this is 25 degrees, and we're going to say that the top of this lovely inclined plane is 2.1 meters. And we're going to actually give our can of soup a mass. And we're going to give our can of soup a mass. And we're going to say that mass is, if it's 8 ounces, it's a half pound. So it's going to be, we're going to go ahead and say it's 0.75 kilograms. Because we all know one thing about cans is that the ounces, liquid ounces, don't necessarily relate to weight ounces, because it's 16 ounces to a pound, but a 6-ounce can may weigh a lot of different weights, because those ounces are volume ounces. So we do have an interest. That's one of the reasons why the English system is a pain in the tushy, is that you got to necessarily know that you've got those differences. So we're going to use a 0.75 kilogram can. We're going to let it slide down, not roll down the plane, because that is a very different. And we want to calculate how fast it's going at the bottom. So if we start at 2.1 meters, we know that the potential energy at the top of our plane is going to equal mgh. We know that that's what it's going to be. Now, I could do a couple of different things. I gave you this height, but somebody else might give you this height. So let's look at what happens if I give you this height. Or not height, that's a length. I give you that length. And let's say that length, for grins and giggles, because I don't think it matches my 2.1, all right? I don't think it matches my 2.1. That this length, say, is 5 meters. If that's 5 meters, we know I can calculate this side. And that side, remember, is going to be the height is going to equal the length times the sine of the angle. Because that's the opposite. This is the adjacent. This is the length. Wrong. This length would be that right there. That would be the hypotenuse. That'd be the hypotenuse. That'd be the length of the plane. So if I'm going to do this, I'm not going to use sine, I'm going to use tangent. Opposite over adjacent gives me the tangent. So depending upon what variable you're given, it's going to depend on how you're going to work through the problem. So you can see this problem a couple of different ways. We can see it as the length of the ramp. We can see it as the length that this part. We can see it as the height. But this case, I've got the height, so I'm going to use that. So my potential energy is equal to mgh. I'm going to leave it that way for right now because I gave you a piece of extraneous information. Anybody know what the extraneous information was? If I'm wanting to find the velocity at the bottom, anybody know what the piece of extraneous information was? No, well, this time it was because I gave you the height. So the angle was, but I gave you another piece of extraneous information. I think I heard weight. It's mass. I don't care what the can weighs. I don't care what the mass of the can is. Because total energy at the top equals the total energy at the bottom. At the bottom, we're all going to be in kinetic energy, and that's 1/2 mv squared. So at the top, I have mgh. At the bottom, I have 1/2 mv squared. Masses cancel. So this doesn't matter if I have a 0.75 kilogram can. It doesn't matter if I have an 8-pound bowling ball. It doesn't matter what I've got up there as long as it's sliding down the ramp. Okay? As long as it's sliding down the ramp. The other thing that we've disregarded in this one is we've disregarded friction. I've not worried about friction in this problem. We've assumed it's a frictionless surface or friction, or these two materials are going to allow it to deal with whatever we need. We've made that assumption. So now if I do mgh or gh is equal to 1/2 v squared, we see this over and over again. We've seen it several times. I've got that, so then I take the square root of 2gh is equal to v, and now if I plug in my numbers, I get 2 times 9.8 times 2.1. And if I plug that into the calculator, take the square root, 2 times 9.8 times 2.1 gives me something on the order of 6.4 meters per second. And we're going to see this problem again, but when we see it again, we're going to be talking about the can or the ball rolling down the inclined plane. So we're going to add some complexity to it. Everybody follow it? Okay. Now we're going to do more fun. So now what we're going to do is we are going to use, we can do it a couple of different ways, okay? We can look at it as, but we've all seen this kind of toy, whether it's in a pop gun, whether it's in those little hopper toys, and you know, given that it's getting to be Halloween, a lot of people do those little popper things. The popper spider, everybody with the little suction cup has a little spring. You put this little spider down and the spider hops, or the frog hops. Frogs are good. I've got smiley face ones in my office. So we do the little hopper thing. So we have a ball, and we're going to give you that the spring constant in this case is a 10 Newton meter spring. Because remember, the spring constant is dependent upon the material. Also remember how I can calculate a spring constant. If I give you that I have a spring, and then I put on it a 50 gram mass, and we measure the change in length. Okay, measure the change in length. And let's say that that change in length is 10 centimeters. I can calculate the spring constant. Because remember, Hooke's law says that the force is equal to minus kx. This case, I've got mg, and that's negative because gravity's going down, so that's where my minus kx comes from. I've got k, and my change is going to be 0.1 meters because I had 10 centimeters. So my x's cancel. K ends up being my 0.1 meters divided by my mass, which is 0.050 kilograms. And I end up with my gravity 9 point... Did I do that right? No, I didn't do this right. My units are telling me something different. It is Friday. I want mg divided by my change in length to give me k. I had it reversed. Because k is going to be in Newton meters, that's how I knew something was wrong, because I had kilograms in the bottom. So I'm going to put my mass in, 0.050 kilograms times 9.8 meters per second squared. There's my Newton. Life is good now. 0.1 meters. There's my Newton meters. So now I can plug that in. 0.050 times 9.8 divided by 0.1 gives me a 4.9 Newton meter spring. So you can calculate the spring constant. But in this problem, I gave you the spring constant. Okay? Gave you the spring constant for this spring. We're going to compress the spring. And we're going to compress this spring. Let's go ahead and do it 0.025 meters. So 2.5 centimeters. We compress it an inch. Because remember, 2.54 centimeters is equal to 1 inch. So I've compressed my spring to an inch. We're going to give ourselves a mass here for our spring, our little object. We're going to use a ping pong ball. And my ping pong ball's probably got a mass of about 50 grams. So it's going to be 0.505 kilograms. And we want to know the height that the ball gets to, disregarding air resistance. So we want to know, so we're going to release this spring, and the ball is going to jump, and we want to know how high it goes. We want to find this height. And we're going to disregard air resistance. So it's going to be the same type of problem if I do the do a little dart out of a spring levered gun. We want to know how far it goes. Can be a bow, because what we're going to do is we're going to look at the energy in the spring. And we saw on Wednesday that that energy is equal to 1/2 kx squared. Here comes the real fun part. We can actually calculate not only the height, but we can calculate the speed at which the ball leaves the spring. Okay? You can calculate the speed at which the ball leaves the spring. We'll do that next. But for right now, we're going to calculate the height. So the energy that I put into the ball by conservation of energy, if I disregard air resistance, has all got to go into letting the ball jump up. So we know that it's going to be that the energy at the top. And we know the energy at the top is only potential energy now. And that's equal to mgh. So now I can take my 1/2 kx squared is equal to mgh I'm solving for h, so I'm going to take 1/2 kx squared divided by mg is equal to h. Hopefully I've done it right. We'll find out. I'll look at my units to make sure. So I'm going to put in my 1/2. I've got k is 10 Newton meters. My x was 0.25 meters squared. Let me do it on a different piece of paper so that it's nice and clean. And you guys can see it. So let's get back here. So I've got 1/2 kx squared divided by mg. 1/2, and we said it was a 10 Newton meter spring. We have a 0.025 meters, and that's got to be squared for compression, divided by our mass, which was 0.050 kilograms. And we have gravity 9.8 meters per second squared. Okay, so let's look at the units, make sure we have it correct. Kilograms meters per second squared are newtons. So my newtons are going to cancel out, so that all goes away. This will end up being meters squared, and that's meters, so I end up in meters, so I've actually rearranged it correctly, so I'm in definite meters. Now we get to plug it in the calculator and see where we're at. So I'm going to start with the 0.025 and square it first. That way I don't get calculator problems. Multiply by 10. Divide by 2. Divide by 0.050. And divide by 9.8. And this looks like, I don't think that's right. We'll look at it again. 0.025 squared times 10 divided by parentheses 2 times 0.05 times 9.8. Yep, that's what it gave me. This one didn't go up very high. The number it gave me was 0.0064 meters. Yeah, that's what it gives me. So my numbers weren't so great. In that case, my numbers weren't so wonderful fun. But that's how you do the problem. I don't usually like just pulling numbers out of the air because that's what ends up with, and this doesn't look good. Because we know that if I have a decent spring, this is actually a fairly weak spring, which is probably why the numbers turned out the way it did. If I do a fairly strong spring, we get those things to bounce way up high. All right. So let's do one with friction. And my one book does it like this. We're going to use an ambulance attendant pushing a hospital gurney. Okay? Got an ambulance attendant pushing a hospital gurney. So let's make our little hospital gurney here. We got our poor person on the hospital gurney, has had a bad day because we're on the hospital gurney. Okay, and we got our other person pushing the hospital gurney here. Nobody ever said I was a very good artiste. Okay, and we're going to apply a force of 100 newtons. And we've got to push this thing 5 meters. And we don't know the friction. We're starting from rest. Okay, we're starting from rest. Let's see. And we're going to have a speed of 1 meter per second. And the mass of the gurney with the patient is 80 kilograms. And we want to calculate the work due to friction. Okay, we want to calculate the work due to friction. So basically, what we've got is that the energy total is going to equal my change in kinetic energy, because remember my work energy theorem. I've got a change in kinetic energy plus the work done to friction. Okay? The total work done is the force times the distance. So I got my change in kinetic energy, my work due to friction, and that's my initial work. So the force, because we're told the force, okay, we're told the force is 100 newtons. My distance is 5 meters. My change in kinetic energy is 1/2 the mass. Velocity final squared minus velocity initial squared plus the work due to friction. We know what that is. We know the mass, so this is going to be 80 kilograms times my final velocity, which was 1 meter per second, and we got to square that. Now I get the work due to friction. Now I get the work due to friction. So if I plug that in, I get 500 newtons. This becomes 1/2 of 80. That's a 1 squared. So this becomes 40. This is joules. This becomes joules plus the work due to friction. Subtract that out. I get 500 minus 40 gives me 460 joules is equal to work due to friction. So I did most of my work in order to overcome friction. Friction is a pain in the tushy. Friction helps us out, but friction really kills us. And friction really, if I'm doing something from a mechanical point of view, if I'm building engines, if I'm building roller coasters, if I'm building a lot of things, I lose a whole bunch of energy due to friction. Because let's look at efficiency. If I look at efficiency, that's going to be the work that went into what I want to do over the work done times 100%. So in our problem here, the work done was 500 joules, right? The work that actually went into moving the patient, that actually did what I wanted to do, was only 40 joules. That's not very efficient. That's not very efficient at all. That's ooky. So I did a heck of a lot of work to do a whole lot of nothing. Sorta. Anybody know what the efficiency of a car engine is? That would be nice. I'd like that.
It's like less than 20, isn't it?
It depends on your car. I think the Carnot cycle gets you the best you possibly could do is about 45%. The best you can possibly do. A lot of them, it's around 30, and now it's a little better. I mean, we do a little better now, but historically it's really crappy. But it actually works out to our advantage. So, I mean, efficiency, we look at efficiency a lot because things are not very efficient, and that's one of the reasons why we want to overcome friction to the best of our ability. Now, again, we got to have friction because I can't walk across a slick floor without some kind of friction because I have nothing to push off of, right? So I can't do things that are totally frictionless, but I want to make sure that I'm getting the best bang for my buck. So when we're building, that's why when we build roller coasters, you think of the steel on steel, or that's why those really pipe roller coasters where I don't have a whole lot of friction in them, because I want to keep as much of the energy doing what I want to have happen as I possibly can. So efficiency becomes a real problem for us. But here's the other fun part. So now we know the work due to friction. So we can do a couple of things, okay? One is we can calculate the force, okay? Right? Because remember, work is equal to the force times my distance. And if I want the force due to friction, I'm going to use the script F. Oh, I don't know if you guys saw it, because it is midterms, right? And everybody's been taking these midterm tests, right? And my daughter posted this too. How many of you have had Scott Haywood? Yeah, you guys had Scott Haywood, right? If you ever watch Scott Haywood's Facebook, it's kind of entertaining. But my daughter's friends with Scott Haywood on Facebook. And so she posted on his, and it says, "Can you grade my test on a curve?" And the person said, "Sure, I'll grade your test on a curve." And the reason this came up was my script F, because they did a very calligraphied F as the curved grade.
Can you curve my grade? Curve that.
Yeah, it's entertainment. So we got my force due to friction. So we've got our lovely curve there, and we got our distance. So we got our lovely distance. So we found out that our work due to friction was 460 joules. That's going to be our force due to friction times the distance. We know the distance that happened, so I can take my 460 Newton meters, because that's my breakout of my joules. My change in distance was 5 meters. And that's going to be equal to my force due to friction. And if I do that, I take my 460 divided by 5, and I end up with 92 newtons. Now guess what we can do? We can find out the net kinetic friction, because this is moving. So it's not static friction, it's kinetic friction. Because remember, friction is equal to the coefficient of friction times the normal force, and we were told that we had a mass of 80 kilograms, which was the gurney plus the patient. So we know the normal force is going to be our 80 kilograms times 9.8 meters per second squared. Gives me 80 times 9.8. It's going to be like 79 or something. It gives me 784 newtons. So I get 92 newtons divided by my 784 newtons is going to give me my static or my kinetic friction, because we're moving. Gives me a 0.12, and this is unitless because my newtons cancel, and that's a coefficient, and we know that that's Newton, or that's out there. So it gives me 0.12. Actually, that's not a very high frictional friction surface. So it doesn't take much to be losing a heck of a lot to friction. Doesn't take much to be using a heck of a lot to friction. So we do have some issues there. So we have some issues. So let's kind of look at it a little bit different. Let's look at, let's take it a little bit in there. I'm going to convert just so that we have it to play with. Let's see if I've got it in here. Hang on. Okay. Because for you medical types or biology types, we don't like to use joules. So let's keep our numbers here that we've got for our person on our pushing the gurney. The total work done, because we had a force of 100 newtons. We had a distance of 5 meters. So the total work done was 500 joules. We had the work due to friction was 460 joules. We had the actual work done for our efficiency problem was 40 joules. So those are the numbers that we got floating around. We got the mass is equal to 80 kilograms, just so we keep our numbers out here. And we have a velocity at the end. The velocity final was 1 meter per second. Okay. If I'm in biology or in chemistry, I don't usually work in joules. I usually work in calories, because that's the number that we have. One of the reasons we work in calories is because it's really easy. The definition of a calorie is to raise water 1 degree C, 1 gram of water 1 degree C, or 1 degree Kelvin. So I have that. So I want to convert our work from joules into calories. So the conversion for calories is it's 4.19 joules per calorie. So it's like 4.18, or we can do that. I'm going to use the 4.19 joules per calorie. So if I do that and convert these to calories, I'm going to take my 500 divided by my 4.19. It says this was approximately 120 calories. 460 divided by my 4.19 is about 110 calories. And my 40 divided by my 4.19 is about 10 calories. Okay? So these, if you plug it into the calculator, you'll find that this one is like 9.5. You'll find those are just a little off, but we're gonna use nice round numbers, and we're gonna be in calories here. Okay. The other thing we know about calories is this is a heat calorie. That's a heat calorie. That's not a food calorie. Food calories are what we call kilocalories, and they're 1,000 heat calories. Okay? Because what we want to calculate is the power required to do this. We want to know the power required to push the patient. And let's see, how many, I have sports players in here, right? Those of you who play sports, raise your hand. And you all know how many calories you burn for a particular amount of sport, right? Because we can go to a table. I always love this, right? Go to a table. The table in this handy dandy book over here that I have is pretty cool. In the handy dandy book, it says, okay, remember that we're talking food calories here. Sleeping. There is power required to sleep, all right? There is energy burned while you sleep. And for people, it's 1.2 kilocalories per minute, according to this table that I have. If you look at your Google app, you might find something a little different, right? My Fitbit, I'm not sure what my Fitbit does for conversions. Sitting, while you guys are sitting in here, now this is unfair. This is really unfair, because this would assume that you're just sitting in class not doing anything. This is physics class. You are burning more calories sitting in physics class, if you're paying attention, than you would be if you were just sitting there doing something else, because the brain uses a heck of a lot of energy. And for those of you who are into the keto diet, I found out something interesting. My son is actually a psychology major, My son is actually looking at a lot of brain chemistry as part of the psychology major, and he says the keto diet is actually one of the worst for your brain. Apparently, the stuff that you do on the keto diet, which is actually good for a lot of the rest of your body, is how your brain has to deal with the amino acids and stuff that it needs, and the energy that the brain needs, the keto diet doesn't really supply and becomes very inefficient, and apparently it's not really good for your brain. We had an interesting discussion about that. I thought that was interesting. Okay, totally interesting. But sitting at rest is 1.7 kilocalories per minute. If I'm walking slowly, it's about 3.8 kilocalories per minute. Cycling is about 10 kilocalories per minute. Playing basketball is about 11 kilocalories per minute. It doesn't have in here it doesn't have soccer in here. Sorry, guys. I got playing tennis. So for this problem, we're going to use the playing tennis one, because if I'm a hospital attendant and I'm trying to get somebody to the ambulance, I'm probably moving fairly quickly, and I'm probably thinking on the tennis side. So I'm going to use tennis, and tennis is 6.3 kilocalories per minute. And if anybody likes follow cycling, Tour de France racers, I kid you not, they really do. I've seen it happen. A cyclist who is doing professional cycling, they list it as 25 kilocalories per minute. When they are training and when they are cycling, they are literally eating on the order of 10,000 to 15,000 calories a day. That is a heck of a lot of food. It's a heck of a lot of food. It is a challenge to cook for that. And if you really want to see something interesting from sports medicine type thing, there is a series on Amazon Prime called Eat, Cycle, Win, or Eat, Race, Win, that follows the food person, the nutritionist that follows one of the cycling teams through the Tour de France. Really interesting looking at it from a sports medicine point of view. All right, so we're going to use the 6.3 kilocalories per minute. We have the work done was 120 calories, and those aren't kilocalories. Okay, we got 120 calories, and we want to know, let's use the time, let's figure out the time that it took to push the gurney. So power equals energy over time. We've got it that we're going to use, where the energy that we're going to expend, or the activity that we're expending, is 6.3 kilocalories per minute. So I got to put that into calories, right? So I got to take my 6.3 and I got to multiply it times 1,000. So that gives me 6,300 calories per minute. So this time I'm going to rearrange it, and I'm going to put time is going to be energy divided by power. And now my energy that we did was 120 calories. The power that we applied was 6,300 calories per minute. Minutes will end up on top. And we did it in about 0.02 minutes. So the guy did a lot of work out there and went out and pretty quick. And again, it's only 5 meters, so we're not in too bad a shape. We're not in too bad a shape. But we can do a similar problem. Let's do the cycling problem. So if a person, I love this one. if a person who normally requires an average of 3,000 kilocalories of food energy per day has a bad day, goes and eats, we can use a Chili's Big Mouth burger. Anybody look at the kilocalories on a Chili's Big Mouth burger? The kilocalories on a Chili's Big Mouth burger is about 1,100 calories. So if you actually look at, and that doesn't count some of the extras that go on it. So if you look at, Carl's Jr. meal, that includes the burger, fries, and the soda, that's actually the sugared soda. If you look at that, you're looking at about 1,200 kilocalories. So let's say you do 2 of those burgers, you're over 2,200, and of course the federal average recommended daily allowance is 2,000 kilocalories. But let's say the person goes out and has a bad day and eats 4,000 kilocalories. We want to know, and we don't want to gain weight, okay? Don't want to gain weight. And we want to know how many minutes we want to be on the bicycle, be it the stationary bicycle or an actual bicycle, in order to burn the extra 100 or 1,000 kilocalories. We want to know that. So I go to my handy dandy table and I said, all right, we're going to do cycling, and we're going to use an average for cycling. And we're going to be slow. We're just going to sit there on the little spin cycle in the gym, watching the news or watching Roadrunner cartoons, because it's kind of fun to watch Roadrunner cartoons. And so we're going to use a value for cycling slow. And if we use the value for cycling slow, we're doing 5.7 kilocalories per minute. So power, again, is energy divided by time. So I can rewrite this as time is equal to energy divided by power. So now I'm going to do my 1,000 kilocalories divided by my 5.7 kilocalories per minute. It's 175 minutes. Think about that. That's like 3 hours. You guys didn't know you were getting nutrition class in physics, did you? The other one, have you guys over in Tonkawa, or the guys over here, done the work lab with the scale and gone up the stairs yet? Have you guys done it over there? Okay, Tonkawa's done it. The energy required, or the work that you did running up and down the stairs, doesn't even burn off a lifesaver. Because the typical lifesaver is 10 kilocalories. Yeah. So it's kind of entertaining to look at that. Alrighty, guys. I don't have any other problems. We're going to start the next chapter next week. I got to get grade checks for you guys over here. We see you on Wednesday over there. And we should be back in our regular room on Wednesday. They got it fixed.